Hello everyone. In this lecture we are going to discuss one more very important topic of analog electronic circuit, and that is voltage divider bias configuration. So in the previous two lectures we have already covered fixed bias configuration and emitter stabilized bias configuration. We have seen the advantages and disadvantages of fixed bias configuration. We have seen how emitter bias configuration provides better stability as compared to the fixed bias configuration. So this is the configuration, or this is the circuit for voltage divider bias configuration. Now, as in case of fixed bias circuit or configuration, we don't have any RE resistance in the emitter terminal. Then we have discussed emitter bias configuration, where RE resistance was connected in the emitter terminal, which generally provides stability to the circuit. In the same way, in the voltage divider bias configuration, the same RE resistance will be connected in the RE terminal, emitter terminal, but the RB resistance will be replaced with R1 and R2, a voltage divider configuration at base terminal. So this particular two resistances R1 and R2 provides voltage divider. So let us begin with the introduction part. Now there are two methods that can be applied to analyze the voltage divider bias configuration. The first method is exact method. The second one is the approximate method. The exact method can be applied to any voltage divider bias configuration, and the approximate method can be applied only if specific conditions are satisfied. Now, the approximate approach permits a more direct analysis with a savings in the time and energy. It is also particularly helpful in the design mode. All in all, the approximate approach can be applied to the majority of the situations and therefore should be examined with the same interest as the exact method. Now, what exactly an exact method? Here we don't have any conditions, so it can be applied for any kind of numerical. So the input side of the voltage divider bias configuration can be drawn as shown here. The R1 and R2 are connected with VCC. So this is the diagram of input side. So what we need to calculate is, we need to calculate the Thevenin equivalent of this particular circuit. So let's see how to calculate. In case of Thevenin equivalent, we need to calculate two parameters: the Thevenin resistance RTh and Thevenin voltage ETH. Now, during the calculation of Thevenin resistance, we need to short circuit all the voltage source available in the circuit. So in this particular circuit, we have only voltage source available is VCC. So we have short circuited this path. Now when you look into the circuit from this side, then we can see the equivalent resistance RTh is equal to R1 parallel R2. Now RTh is equal to R1 R2 by R1 plus R2. So this is Thevenin resistance. Now let us see how to calculate the Thevenin voltage. Now during the calculation of Thevenin voltage, the voltage source VCC is written back to the network and the open circuit Thevenin voltage is determined. So this is the circuit, and Thevenin voltage is calculated across the R2 resistance. Now let us apply the KVL in this area or in this loop. The loop equation will be VCC minus IR1 plus IR2. Let the amount of current flow in this area is I, and I is equal to VCC by R1 plus R2. Now let us see what will be the value of ETH. It is the current across the R2 resistance into the resistance R2, which is IR2. So ETH, or voltage across R2 resistance, is R2 into VCC by R1 plus R2. So this is all about the calculation of RTh, new resistance, and the ETH, the new voltage. Now, as we discussed in our previous two lectures, every biasing circuit has two loops: the base emitter loop, which is the input loop, and the collector to emitter loop, which is the output loop. We need to apply KVL in the base to emitter loop first. The KVL equation will be ETH, the IB into RTh, then VBE, then IE into RE. So the loop equation is ETH minus IB RTh minus VBE minus IE into RE equal to 0. Now the IE current can be written as beta plus 1 IB, So the equation will be ETH minus IB RTH minus VB minus beta plus 1 IB RE equal to 0. Now in this whole equation we have one common current, that is IB. So we have taken voltage source in one side, LHS side, and all current source, all current part in RHS side. So ETH minus VB will be equal to IB RTH plus beta plus 1 RE, and IB current will be equal to ETH minus VB by RTH plus beta plus 1 RE. And if the transistor is made up of silicon type, silicon semiconductor, then it can be written as ETH minus 0.7 volt by RTH plus beta plus 1 RE. Now this particular current equation or base current equation is very similar to the base current equation of emitter biased configuration. The only difference is we have ETH here, which was VCC in case of emitter biased configuration, and we have RTH here, which was RB in case of emitter biased configuration. Now let us apply KVL in the output loop or collector to emitter loop. Before that, we can calculate the IC current, which is the operating point of IC, that is equal to beta into IB. Now after application of the KVL, the loop equation will be plus IERE plus VCC plus ICRC minus VCC. So this is the KVL loop. Now we can substitute IE as IC. After that, the equation will be VCE minus VCC plus IC RC plus RE. VCE will be equal to VCC minus IC RC plus RE. Now VE will be equal to IE into RE, because the amount of current flow in the RE resistance is IE and the resistance is RE. So VE will be equal to I into RE. So from this we can calculate the VC voltage also. As we know, VCE is equal to VC minus VE. So VC will be equal to VC plus VE. Now VC can also be calculated as VCC minus ICRC. From this explanation, from the output loop equation, we have IERE plus VC minus VE plus ICRC minus VCC. Now VE is same as IERE, so plus V and plus VC plus VE and minus V get cancelled out. We have VC equal to VCC minus ICRC. Now VB voltage can be calculated by this formula, that is VBE is equal to VB minus VE. So VB will be equal to VBE plus VE. Now let us see how to calculate the saturation level values. That means saturation level of current and saturation level of voltage. Now the output loop equation is VCC minus IC RC plus RE plus minus VC equal to 0, and we got VCEQ equal to VCC minus IC RC plus RE. VCE set, or the saturation value VCE voltage, can be calculated by keeping IC current equal to 0 milliampere for an ideal condition, which is equal to VCC. This particular calculations we have already made in case of emitter bias configuration also. Now in the same way, we can calculate the IC set keeping VC equal to 0 volt, that is VCC by RC plus RE. So IC is VCC by RC plus RE and VC is VCC. VC set is VCC. Now this is the VI characteristics of emitter bias configuration. Sorry, this should be the voltage divider bias configuration, but it is very similar to the emitter bias configuration also. We have x-axis, which is VCE voltage in volt. We have y-axis, which is IC in milliampere, the IB current, and the load line, which is which joins IC set and VCE set, and the intersection point is our Q point. So the load line design and the VI characteristic is exactly similar to the emitter bias configuration. Now let us see how voltage divider bias configuration is better. Now in case of voltage divider bias configuration, the R1 and R2 resistance, which makes the voltage divider, provides a good resistance value or RTH value at the base terminal, or we can select the values of R1 and R2 in such a way that it will provide a very good stability to the circuit, or you can say it makes the independent IC current, beta independent IC current. The calculation is very similar to the emitter bias configuration. We have to write the IB current equation, which is ETH minus VB by RTH plus beta plus 1 RE. Now taking beta plus 1 common from the denominator, we have taken common. Now this equation is IB equal to ETH minus VBE upon beta plus 1 into RTH by beta plus 1 RE. Now we also know that IC is equal to beta IB and beta plus 1 is beta. So IC is equal to beta IB. In numerator we have beta into ETH minus VB upon, in the denominator we have beta into RTH by beta plus 1 plus RE. And IC is equal to beta IB. Beta beta got cancelled out. Now we have this equation. Now in this equation we can choose the value of resistances R1 and R2 in such a way that we can make RTH by beta plus 1 very nearly equal to 0, or you can say very small. In that case, IC will be equal to VCC minus VBE by RE by neglecting RTH by beta plus 1. Now the current equation is independent of beta. So from the previous discussion we can say advantages of voltage divider bias circuit is we can make the current equation, IC current equation, less independent of beta by choosing the proper value of R1 and R2 resistance. Now as we know, beta is temperature dependent, so any variation in temperature may change the value of beta. From this equation, IC is equal to beta IB plus ICU. Now output current depends on beta. Circuit current can be made beta independent, due to which the operating point remains fixed or remains stable. So let us see one numerical on voltage divider bias configuration. Now the numerical is determine the DC bias voltages voltage VCE and the current IC for the voltage divider bias configuration as shown in figure. Now in this figure we have VCC voltage equal to plus 22 volt, R1 is 39 kilo ohm, R2 is 3.9 kilo ohm, RE is 1.5 kilo ohm, RC is 10 kilo ohm, and beta value is given 140. So we can calculate the RTH, the equivalent Thevenin resistance, which is R1 R2 by R1 plus R2. The new resistance is 3.55 kilo ohm. Now the Thevenin voltage ETH is R2 VCC by R1 plus R2, which is 2 volt. So the new voltage is 2 volt and the new resistance is 3.55 kilo ohm. So these values can be similar to the emitter bias configuration. IB current can be calculated by this formula, ETH minus VB by RTH plus beta plus 1 RE. So we have put the values to 2 volt minus 0.7 volt, as this is a silicon type of transistor. And finally we got the IB current as 6.05 microampere. Now IC current we know can be calculated by the formula IC equal to beta IB. So IC current is 0.85 milliampere. And the VCE voltage can be calculated by the equation VCC minus IC RC plus RE. So by putting the values of all the parameters, VCC is 22 volt, IC is 0.85 milliampere, which we have calculated. 10 kilo ohm is the RC resistance, 1.5 kilo ohm is RE resistance, and finally VC is 12.22 volt. So in this way we can calculate the parameters of voltage divider bias configuration, or you can say the quotient point of voltage divider bias configuration. We have already discussed, we have also discussed here that what are the advantages of using the voltage divider configuration, how the circuit current can be made less stable of beta. So in the next lecture we will discuss about the approximate analysis of voltage divider bias configuration. Thank you.